Okay, we're ready, right? Okay.
Yeah.
So, what's up, guys? So today, we're gonna go over graphs. So first lesson on graphs, and before I begin, I'd like to say tomorrow is Veterans Day. So tomorrow we're not having a Geary lecture. On Friday we're still doing something, since it's not a holiday. Master's gonna go over more in depth what it's gonna be, but now, our beginner lectures are still happening, regardless of that. The 26th, Geary is done, of November, but
Actually, the 18th. 26th is Thanksgiving, so 18th is Gary's last lecture.
yeah, the 18th is Gary's last lecture. 26th is Thanksgiving, which is a Friday? No, 24th
It
is.
starts Thursday.
Yeah, no, always, but it's the 24th is a Wednesday.
Yeah.
Yeah, okay.
26th is Friday.
Are we having something? Am I doing something the 24th? I still am,
Is
right?
there class?
I don't have class that day.
No, if school is still going, yeah, you do it.
Okay, and you're not gonna do that
No.
stuff. Okay, so 24th, I'm gonna be here. So right before Thanksgiving, unless people don't want to do it, but I'm gonna be here, and it's gonna be on YouTube. Other than that, be sure after today's lecture, I think there's a mobile dev. They have a meeting.
Yeah.
They have one, right?
Yeah.
At 7:30.
Yeah. I'm not sure. They can look at it.
Yeah. So be sure to look out for what mobile dev is doing tonight. Around 7. But anyway, today we're going over graphs, and just to start off with, I'm gonna do DFS. We've been talking about DFS throughout the whole, these lectures, but I've been doing it with trees, and I have not visualized it for you guys. So I am actually going to draw I'm gonna make it, well, okay, actually before I draw anything, do we all know what a graph is, right? How it's represented? Okay, a graph, is like it's mathematics. It's a mathematical notation. It is two things: the list of vertices. It's a good marker, by the way. Just wanted to point that out. Nodes. And the edges. Okay? All right? We good so far? Okay. So it is a list of nodes and edges, and an edge is described as, so one edge, say edge 0 is, say, one vertex or node U that goes to another vertex V. Okay? We cool on this so far? And so we all know the difference between directed and undirected graphs? We do? Okay.
Yeah.
All right. Well, in case people in the live stream don't have any familiarity, this is an undirected graph, so meaning each edge is bidirectional. I can go from here to here, here to here. So I'm gonna make this U and V, arbitrary. So if I wanted to add this in the graph, I would need to specify U to V, and I also need to add V to U. Make sense? Right? Because it has to go both ways. But let's say this was directed, then where's the eraser? Okay. Then we got to get rid of this. If it was directed, with the arrow, going from U to V. But we'll stick with a undirected graph. In fact, let's get rid of U and V as well. And I think I might make this a little bit more complicated. All right. So this is in undirected graph, right? And each node is listed for the graph. So we're going to say that there is, let me get rid of this too. So we have an adjacency list. Do you guys remember what an adjacency list is? Yeah? So an adjacency list has this, right? List. I would make it a map, right? Of each node, node 0, right? And then that's the key, the node is the key. And then the value would be a list of other nodes it's adjacent to. Like say, I could, you know what? I'll just number them. Node 1, node 2, node 4, node 3, node 5, node, what is it, 6? I think there's 7, yeah. So node 0, right? What would be in node 0?
1 and 3.
Yeah. 1 and node 3. Okay? And what would be in, say, node 1?
0.
Yeah.
2 and 4.
0, node 2, and node 4. Right? And so this is undirected, yeah, you have to include node 0 again, right? Because there's technically 3 adjacent nodes. All right? And so on, right? This is a graph. This graph is a list of nodes where each node is corresponding to a value of a list of other nodes that it's adjacent to. This is an adjacency list. And this is pretty much just a graph. This is an unweighted graph, which makes the algorithm simpler, right? So we went over what was it, DFS at one point, right? Do you all remember what DFS does?
So it goes through the graph.
Yeah.
It goes it goes through the depth of the graph.
Yeah, exactly. It goes
As
through the
deep as
depth.
you could go.
Yeah, as deep as you could go, then you go back up, backtrack, and see if there's any other path you could take. Exactly. That is exactly what this is. So let's say I wanted to do DFS on this list, right? So I want to do DFS, right? And let's just say this list is global. Hell, I'm even gonna make a time variable and set it equal to 0. We'll know what this does soon. Okay, so we're gonna iterate through each key or each node in the adjacency list for node in. Oh, another thing.
In the keys?
Well, the node is the key.
No, in adjacency list dot keys.
No, you don't need to do that in Python. When you iterate, well, we could do items. Do you want to do items?
You can do
No,
key as well.
since it's a dictionary, you need to iterate over the keys.
Yeah, but that's by default when you iterate through a dictionary, you're
Oh,
iterating
yeah.
through the keys. Yeah, you get the keys.
Okay.
Yeah. And I forgot about something. Okay, so let's keep some global variables. Time, whatever, doesn't matter. Time equals 0. And color, right? What's color, right? Color is going to be set to W is white. Okay? N1, white, and so on. They're all white. So I'm actually going to put a little W on all of these. Do you guys know why I'm doing this? You guys have any intuition as to why I did this?
Painted other color when you've gone through it.
Yes. This is to just indicate that we have not explored the node or the vertex yet. That's what this W means, this white. So color, they're all white at first, and we're gonna iterate. So I'm gonna write my DFS function for,
You might be blocking him from seeing the code.
oh, sorry.
You can see him.
So for each node in the adjacency list, if color node equals, then I'm going to call the helper. Helper, call it on the node. Okay. All right. So this is not the complete code, obviously, right? This is, I have to write the helper class, the helper function somewhere. Might need more space in this. Does this track my face? Doesn't track my face.
No.
Okay, I'm gonna get the other board. Oh, thank you. I'll get the other board. All right. Do we understand this though?
Yes,
What we're
yes.
doing? Yeah, we get it?
Yes.
Yeah. Thank you, Michael. We appreciate it. Okay. Yeah, put it right there. I'll deal with it. So, all right. Oh, so you can see it all. So we've done this DFS method. Now after this, what do we need to do? We need to write the helper. We'll define it here. Oh, I didn't do define. So I'm going to define the helper method. Which takes in a node. And of course, this node is going to be white. It's going to be unexplored, right? And so time, I'm going to plus equal 1 here to start. And I'm going to color the node gray, right? So let's say we started at node 0. Okay? So this white becomes a gray. Okay? And do you see why we call it a gray? Because we don't want to explore it again. We don't want to recursively call on it. So it's gray. And time, when I got in, was 1. So we're at time 1 at node 0. So now, another thing, right? Now we go for, say, for node in so I need to do something to this. What do I need to put here? Actually, before I do that, adj means adjacent node in adjacency list, but it's not just the adjacency list, right? It has to be
Node.
yeah, of node, exactly, because this node is in there, right? Do you see that? So for each adjacent node, each node adjacent to this one, right? What do we have to check first?
White.
If it's white, yeah. If color node equals white, right? Then I recursively call it again on the adjacent node, right? Okay, so let's say there weren't any, well, it doesn't matter. What do we do after we escape this for loop, right? Have we gone through all the depth? What do you think?
Wait, you said we've gone through like the whole depth, or?
Well, the depth from this node.
Okay, so then we backtrack.
Yeah. So to backtrack, right, we increase time by 1. By the way, time, we remember time is a global variable, right? And we color it, right? We have to color it black. Color node. Color it black. Okay? Actually, let's do it here. All right. So let's follow the logic that we did here. So we went to this node, we did that. Now we go through its adjacent ones. At node 0. So we go through this list. Node 1 is the first one that appears. It's arbitrary. The order is arbitrary, but it doesn't matter. So from here we go here, right? So then we change this one to gray, and the time that it goes in is not 1. What is it? It's 2, right? Because when we recursively call it, we increase the time. So we enter a time 2. Okay. So then we're here, and we look at the adjacent ones, right? So the first one in the list, yeah.
Why doesn't it look at N0?
Okay, so we're here, right? These are all the adjacent ones. Okay? And we're going through the adjacency list of node 1, which is here. And N0 is the first one. Do you recursively call on N0?
No.
And why?
Because we'll be going back.
We'll be going back, but how did we keep track of that?
I think he knows.
He knows, you know.
Oh, yeah, because it's gray.
Yeah, because it's colored gray. It's not colored white. We don't, if it's not colored white, don't recursively call on it. So don't go back, right? Because then you're going to be in an infinite loop. You're going to go infinitely.
Didn't mean to call you out. I just want to make sure everyone's involved.
Yeah.
I'm sorry. We're sorry.
Don't hate me, please.
We're deeply sorry.
Thank you.
We're having fun, okay? Respectfully.
Exactly.
Yeah. Okay, so we don't go to this one. We go to the next one that's white. This one's white. So now we go here. Make it gray. And 1, 2, we enter at 3. So good so far. So good so far. So now we're here, and now we go through all the adjacent ones. And we're going to say that N1 is the first one, just because. And this is gray, so ignore that. N3 is white. So now we go here. It's 3, the time, 4. We enter at node 3 of 4. We change the color of node 3 to gray. All right? And then what do? We go through all the adjacent ones. So node 0 is gray, we don't go. Node 2 is gray, we don't go. Node 6, white. There. So we enter here at 5. And color is gray. All right. Now we're here, right? Now we go through the adjacent ones. Node 3 is gray, we don't go. Node 5 is white, we go to node 5. G, and we enter at time 6. Okay. Again, we already know which one it's going to be. It's going to be node 4. Gray, and we enter at 7. Okay. And now we're going to recursively call on this one, and we see that none of them at all are white. None of the adjacent ones. So then we time plus equal 1. So it's 8, right? So we finish. So the time in which we finish globally is, 8 time units or seconds or whatever, right? So as soon as we come here, we don't recursively call anything. So we're done. So it goes from 7 to 8. Does that make sense? Okay. So now, instead of this being gray, it is black. Now, what does that symbolize? Gray versus black. Black means we are completely done with this. That we have recursively taken this from the stack forever. All right? So gray just means that it's in the stack. And we're just going back. We're going back to all the grays. But we're not going back to any blacks. The blacks are forever discarded. The black. What? What?
Nothing.
What? Did I say something wrong?
Sure. Out of context, yeah.
Oh, I mean, in the proper context, you know what I said.
Okay.
The black nodes.
Make it blue.
Make it blue, yeah.
You know what? It's blue now. All the blues are discarded.
B stands for blue.
Yeah, B stands for blue now.
You're the ones thinking about it. You know, you're the ones thinking
Because I'm
about it.
constantly thinking about this club and our reputation.
Okay. Okay. Maybe computer science needs an overhaul.
Master main?
Huh?
Master/main?
What do you mean?
GitHub? Git?
What about
The
it?
change from master to main.
Oh,
Because you didn't know
it's still master on the computer, like on
that?
the
Yeah, but
Git.
they changed it to main.
They're changing it to main.
Yeah.
Oh, okay. I didn't know that. I don't keep up to GitHub's affairs. Okay, the blues. The blues, because they want me to change it to blue. Okay, all right. So anyway, where did we come from? We came from this one here, right? And here we're pretty much done, right? Change this to blue. Right, we came here at time 6 and we leave at time 9. We leave at time 9, right? So that means that we had to recursively call on other ones. It took some time, and to come back to here, we're here at 9. So it took 3 time units to come back to where we started. So I think this one came from it came from here, right? Make this blue. And node 6, 10, yeah, 10, yeah. It was here. This one blue. We came here at 11, right? If we came from here, right? Make this one 12. We came here. 13. And we came from here. And 14, right? So this is the root. Well, this is arbitrarily the root, right? We started at 1 and we came back at 14. Okay? So that means, right, that we really only recursively call on one node only once. So what's the time complexity of this algorithm?
2n.
Well, but what does 2n really equal? Big O notation. So yeah, exactly. Coefficients are just canceled in big O notation. All right? So this is a linear algorithm. Every node is accessed exactly only once. Okay. So this is DFS. This is also know another thing that the whole white, gray, and blue thing that we did. Yeah. I'm doing this because they told me to do this. And so the white, gray, and blue, the gray thing, we don't need it. You could have just put it as blue, right? The whole point is that it had to be white to be visited. Okay? So I could have just made them, white and blue. You could do that. In fact, me and Lazaro were just discussing that we don't really need to. The only reason I put it as gray was so that you know that that is one node we come back to, right? That's the only reason why computer scientists really do that. That may change. So what's next? What's next? Can I erase this? You think I can erase this? Yeah?
Yeah.
Okay, so I'm going to erase probably just the times and the colors. And I'll erase this too. Well, we're gonna leave it up for a bit. So I'm thinking either number of islands, but you said island perimeter. I think number of islands, right? So
yeah,
there's
easier transition to this.
yeah, I'm trying to because it's DFS. You could use BFS for it too, but I think
Okay.
DFS is much more
Or
practical.
you also just went over it.
Yeah, just go over. So I want to just. So notice that sometimes not all applications of this algorithm will be exactly on this sort of representation of node and edges. You know a matrix, right? A 2D matrix. Technically, that's a graph, right? You're aware?
You said a matrix is a graph.
A matrix is a graph. Yes.
Where are the edges? Like the adjacency?
Yeah, that's it. So, you know what? I am gonna erase it. I'm sorry, guys. I am gonna erase this. I just need space. Do you think I'm gonna have time for? I want to make time for BFS, though.
Yeah, you just do number of islands.
Okay, I'll just do number of islands. So this is going away. So I'm getting rid of this. Yeah, just and this. All right. Yeah, as I said before, looks something like this. It's like that, right? In a way, you can think of it like that. So instead of, there's only two. Well, there could be at most 4 adjacents. And what would you do, right? If you're at I and J,
9?
huh?
9?
What happened?
Like a node can have 9 adjacent nodes.
9 adjacent?
No.
No, so each node has at most 4.
Yeah.
Yeah, exactly. So they have at most 4, right? So it's not a list, it's directions. And you're at position I, J. So you can go to, I think this is I, J plus 1, I minus 1, J, I, J minus 1, and I plus 1J, right, thank you. Do you see that do they see this? On the
Yeah, no, for sure.
So do you see that these are all the directions we need to worry about when we're calling DFS recursively? Because, so actually let me just give you the problem. So, actually and in this instance, we don't need to color anything gray, we'll just color it blue, right? So we're given a matrix kind of like this. I think it's level. It's not level. Okay. So 1 is land, 0 is water, right? And what is an island, right? An island is a collection of ones such that they are surrounded by water, or, they're all. So I'll give you an example. You're supposed to count how many islands there are. So how many islands are there? I'll give you a hint. This is one island. This is another island. Okay, because they're all.
How are the islands?
Because 1 is land and 0 is water, right? And see how these two are disconnected because there's water between.
Oh, okay, I see.
You see it now. And then we have this one. That's another island. as another island. Okay? All right. And this is a DFS problem because what we're going to do is that we're going to, at the outer one, remember the outer DFS, we go through the, we're actually going to go to each one, right? And find the first land that's 1. Do you see how we do that? You're confused?
Wait, what do you mean? Wait,
Okay.
what are you saying we're doing? We're finding the first land that's
Yeah,
1.
exactly. And not only do we need to do that, we need to do a few things. So I'll actually, so I'm gonna put, I think, what are the arguments? What are the arguments that they asked for?
The number of islands
Yeah, you look at it really quick.
should just be the matrix.
Just the matrix?
Yeah.
What do we call it? Just grid? Grid? They'll call it grid.
Yeah, they usually do matrix and grid.
Yeah, so this is the grid.
Yeah.
Oh, it's map?
No,
No, but map.
it's like an island in water.
Yeah, but map.
Yeah, makes sense.
You know what? Fine, I'll call it.
Making it up now.
No, it's okay. We'll call it map. I'm the map. I'm the map. So the map. Yeah. You like map.
They called it grid.
They do call it grid, right?
Yeah.
Well, I'll keep it map because he wanted me to put map, and I'll give it to him. Okay. So I got 9 islands map, right? So what do? We need an answer. So the answer at first is 0, okay? Because at first, there might not be any islands at all. So that's the root case. So what do? We iterate. For I, go through the rows, right? In range, the length of the map, how many rows there are. Then for j in len what does that mean? That's how many columns there are. You see that? Okay. So what do? So we have to check something. So when do we actually find an island? When there's land. So we're at a position in the map or the grid where we find the 1. So if map I j equals I guess 1. If it's 1 plus equals 1. Okay? And then leave it like that. All right. Is that it? Am I done?
No,
Why am I not done?
because you're only counting the ones.
I'm only counting the ones. So that will,
They might be connected.
yeah, that's the thing. So if these were all just ones disconnected from each other, like a checkerboard, like 1 0 1 0 1 0, yes, there will be this many islands. But see, here's the DFS part. We are actually going to mark. So let's say we land on land. We're on land. We're going to mark all the adjacent ones that are 1s and put them either at 0 or 2. 2. I'll say they're 2 to say that they're explored. So I'll do on map, and I will put the position where I'm at. Okay? And helper I'm going to define right here. Helper oh yo. Is that Lacoste? Yeah, we're like Okay, so what do we need in our helper, recursive helper function? What do we need? We need our base case, right?
I think Hermes knows.
Hermes, do you know what to do here?
Sorry, repeat the question.
Okay, so basically, I'm gonna explain it really briefly to Hermes.
No,
So-
no, he does need explanation. He's good.
Yeah,
Just-
yeah, just like quickly.
But just in case, I want him to get the full context, right? Because he does know how to solve it. But see, a 1 is land, 0 is water, right? And we're trying to count how many islands there are. And it's a 2D matrix. So, it has rows and columns like a 2D matrix. Like this, the map. So you need to count how many islands there are, right?
Right.
So how many islands are there? Well,
There's 4.
yeah. So we need to...
That's one.
That's one. So see? So whenever I find land, I just increment. But I need a recursive helper function, which this is the DFS part, right? I also explained to them that a 2D matrix is technically a graph. Do you see why?
No, I knew that from prior. No, I don't see why.
Well, the reason is because each coordinate is a node or a vertex, right? And the adjacent one is like an edge to the next vertex, right? And a graph is just like a map, much like that. It's a square graph, right? But anyway, so we're a helper, right? We call it on map and the position, right? So what do we need to check? We need a base case to keep it from being recursive. So I could just write one if statement that if that if statement runs, it'll run everything. But if that if statement fails, it won't run it at all. So it'll stop recursively calling. Okay, so what do we need to do? Actually, let me represent it this way. Let me change it up a little bit. Let's say I land here. Okay, I think this makes it. Oh, then this is all an island. Okay, it doesn't matter. So here's our plan. I'll start here, and then I'll go to the code. So now I think there's 3 islands. But how do we determine there's 3 islands? Okay, so basically, right, this is the first one we find, right? And then we're going to recursively traverse, the islands. So, let me do this for now. Let me use blue. I'm here, right? So there's 4 directions I could take. I can go up, down, left, or right. You see that? Okay? So if I go up, what happens? You have gone out of bounds, right? So this is one thing you have to check. Or maybe I go down, I'm here, and if I go down, I'm out of bounds. So this is an important part. I have to make sure I'm not out of bounds for my position. So if I'm out of bounds, I stop the recursive call. Okay? Let me put it here. So what am I checking, guys? Help me out here. What do I need to put?
Hold on, sorry, before you continue, so the A and S, so like I guess answer, basically, I guess what, that's keeping track of how many ones we have?
That's keeping, well, at first it was, but then I put this, and now it's just gonna keep track how many islands. So all the ones that are connected and are adjacent, they're all gonna be combined. They're gonna be joined. So that's what this is. This is supposed to join them, right?
Oh, I guess it's supposed to join like the ones that we have.
Yeah, the ones that are together, right? So like
okay.
all those ones are gonna be like the same island, right? So there's something we need to do, right? So what did we just say? We have to make sure that I and J are. Oh, let me put this in front of the camera. We need to make sure that I and J are actual positions. So Make sense? Right? Needs to be greater than 0 and less than the length of the map, which is the number of rows. So, and what else? Yeah.
For the map, if you do the index 0, what is that gonna return?
Index 0?
Yeah. Just like I see.
Well, 0 is a valid index in any array in programming. What?
I just mean in general, like the map.
Yeah.
Oh wait, what?
This is an if statement that
Oh, map is the array. Okay.
map is the, yeah, it's the 2D array.
I
Yeah.
thought
What?
it was like the map function in Python.
See, that's why I wanted to call it grid, right? Because I would cause that confusion. The map is a reserved word. Yeah.
But then why don't you do like map I or whatever, and then if that one is.
Map I. Okay. I mean,
Never mind.
you actually have, no, because you're gonna get an index out of bounds, which is the thing I'm trying to say. We're not trying to get that error. We don't want to index. So see, we're making sure that we don't get an index out of bounds. So what about J? What do we need to check for J? Same thing. Yeah? Okay. All right, so basically this is the out of bounds part. There's another part that we need to check. Okay? So let's say from this one I go to the left. What happens?
0.
Yeah, 0. That means there's water. So that means this isn't part of the island, right?
And?
Yeah, and. Yeah, and.
It's not or?
No, because, well, it has to, I has to be between the range and j has to be between the range, so that when I access a value, ij, it's gonna
I
be
see.
suitable.
Ooh, I see. Okay, I see what it's doing.
Yeah.
So you can do everything within that.
Yeah, I'm gonna do everything within that if, instead of the other way where it's like if it fails, then I return. No, so all these needs to pass. So let's say I'm at 0, right? So that means I don't call it. So what do I need to check when I go to the next position? That it's land. So what's the check? And what else? I don't think it's map I j equals 1. Okay? So only recursively call this if all these pass, right? Because if I'm out of bounds or I haven't, like, I'm not on undiscovered land, then I can't use that. I can't join. So that's like, you stop calling the recursive function. Make sense so far? Are we good? Okay. Okay. So 1 means what? It means that it's land, but let's analyze the structure, right? So 1 means it's land we have not discovered yet, and we're seeing it for the first time. Wouldn't you say? And this 2D matrix is mutable. We can change values in it. So what can we do? At the position we're at, we found undiscovered land. What is it now? To discovered. So we could change map at ij to 2. At this point, like, right? So, well, I'll just show it here. So let's say I'm here. I think I say this. I change this to 2. I change this to 2. 2.
One big island.
Hmm?
It's one big island.
Yeah, this is one big island. Yeah, I kind of mix it up and I combine them by accident. Yeah, so they're all just combined. This is a big island, guys. This is Greenland. It's 2. Did I? think.
Yeah, no, that makes sense.
Okay. All right. So this is one big island. This is Greenland or Australia.
Africa. Oh, it's on that island.
Africa is an island?
No.
Technically it is.
Technically, all land masses are islands.
Yeah, all land
Oh.
masses. Exactly.
Okay. So basically, let's say I'm here, right? Do I keep recursively calling? No. I'm done recursively calling because I'm surrounded by zeros and twos. So that's it. It all goes back to the beginning, and all these were turned into twos, right? So I finished the, well, actually, I didn't finish it here. I didn't finish it here. So this is a helper. It takes in position. So what do we need to do? What positions do we need to take? I call it again. Map. And what? What did I say? I could do I minus 1, j. So this is going up a row, or back a row. I plus 1, j. So I'm going down a row or forward a row. Disregarding the rows. Go back, go to the left.
Should have put that in an array.
What do you mean?
Like the directions.
This is simple. This is fine, Lazaro. This is fine. This is greedy.
Is it pretty?
Yeah, it is actually pretty. Yeah, Lazaro's gonna show us how to do this neatly, somehow.
Just put it in an array, the directions.
This is fine, Lazaro. This is okay. This is fine. Yeah, right? This is fine. I know what you mean, but I mean, this is just a, I mean, we're only moving in 4 directions.
Dude, please do it in an array.
No. Look, Lazaro wants me to put
If
this.
you did that in an interview, they will roast you.
I hate you.
How much I love you.
I know. It's the same lines, though. It's the same amount of lines. It's only 4 directions, too. It's a finite
Actually,
amount.
It's less amount of lines. It's half that. It's only 2 lines.
Okay, fine.
Oh, take into account the array, 3 lines. Globally set that.
I'm going to put it here because this is impromptu. So, shut up, shut up. 0, 1.
You do like right, gives you the correct. Thank you, David.
Fine, whatever. So for each direction, helper, map, my knee hurts. Dir 0. Okay, fine. I satisfied Lazaro, right?
You always do.
Yeah. So I got directions, right? So the row stays the same in 2, but no, wait. Is it? Yeah. So the row stays the same in this case, but you can either go to the right or to the left. Then you could either go up or down. And that's this. So for each direction, I'm just going, say, up. Oh, well, this could be 0. This could be 0. This could be 1, -1, 1, -1. So, okay, yeah, it is one less line of code. Okay, whatever. So this is how you do it with an array. Okay. So let's say I do this, right? And I stop recursively calling it, what happens? When I stop recursively calling it and I'm back to the main function here, well, not the main function, but this function, what happens, right? So I'm back to iterating, row-wise. I'm here, right? I'm back here to where I started. I keep going. Do I call on this? Do I call on this recursively?
Yeah.
No.
Yeah. Wait.
Are you
why,
sure?
why don't you do that one? What do you mean?
Well, look, doing the when we recursively call on this one, it turned all the adjacent ones to 2. And what's this check right here?
Oh no, because no one.
It's not 1. This is land where we have discovered, so we don't care. We've already discovered all that land, and they belong to one island.
Because we did the for loop, and we went through the for loop of that, and we did that.
Yeah, we went to the ij. We said it was 1. We call the function that's recursive, and we do all this, right?
So the helper, all it does is change like the adjacent land to 2.
Yeah,
So
all the
you're
adjacent
not
ones.
1 to ends because it won't be 1. It'll be 2.
Okay, but ands is being affected not in this recursive.
No, I know, but
Yeah.
like since it's not 1.
Yeah, you don't add, yes,
it's not
exactly.
1 to end.
So this doesn't affect ands since it's 2. It's not 1. So I keep going, I keep going, I keep going, okay, I find this one here, ands is incremented to 1, and this is 2. And all the adjacent ones are 2. Got it? Okay. Same thing. All right. Recursive, I go back to where I started. I do, this one. To get 2s, ands is incremented by 1. Huh?
When did you get to that one? Did you get it while you were in the helper function or in the?
Okay, so when I got to this one, I called the helper function, and I recursively called all this. Then I got out of the recursive helper function back to the main num islands function. You guys see? And then I go back to going by row, going row-wise. So I go here row-wise, I find that's a 1, then just get the island, increment. Then I go back here to this 2, and it's a 2, and it's discovered, so it doesn't affect the answer of, it doesn't affect the answer. I don't increment. So how many islands did we find in this case? 3. There were 3 islands. And this is how you solve it. And what's the DFS part? Which one's the DFS part? What makes this a DFS problem? Why is it DFS?
Because you're going into the depth.
Yes,
Island.
exactly. You're going into the depth, right? You're going all the way down, right? And you're also marking positions you've already visited, so you don't recursively call in it again. Like in depth research, yeah.
So you can do DFS and BFS like apart from trees.
Yes, you can, totally.
Graphs in general.
This is a graph.
This is structurally speaking, this is a graph. Each position is a vertex or a node. Sound good? How much time do we have left?
15.
15. I wanted BFS.
Alright, go for it.
Okay, so this can also be solved with BFS, although I don't know how, actually. Yeah,
You
I actually don't.
get out of here.
Oof. I should change these values, right? No, wait, actually, I'm gonna go back to the graph I had before.
Paulina said instead of changing it for 2, can it just be 0?
Yeah. So I just chose 2 just because that was my preference. But yes, you can totally just say it's water, right? And ignore explored land like it's water, and don't count it as part of another island, even though it's part of the same island you already visited. Okay? Yeah, Paulina's right. So I'm gonna make probably the same thing. Yeah, make it simple this time. So DFS was recursive. Well, DFS, you can do it non-recursively using a stack. Yeah.
What was the time complexity?
Of what? Oh yeah, what's the time complexity of this, guys?
N squared.
Yeah, and
Yeah,
square.
it's n squared.
Well, if the number of coordinates was your n, it would be n, right?
What?
If n was the number of coordinates, so you know. I mean, no, it's not n squared actually. It's n by m. N rows, m columns. Okay? Because you're going through all the rows and columns.
But also you're going like to every connected land.
And then you go back.
Yeah, so it makes it complicated,
N
right?
by n squared.
So it's like n squared by m squared?
Yeah.
Not really though.
It's n by m squared. N m squared.
Okay.
Yeah.
Because you could be going through,
Because that outer for loop, right? You're
Yeah.
going over everything. When you're DFS, the whole thing could be an island as well.
yeah, the whole thing
So
could be
worst
an
case
island.
scenario, you do that twice.
No, so it's n by m actually.
But you
Times
do
the
it twice,
constant.
Yeah,
no?
the whole thing is an island is n times n.
Yeah, so that DFS is to go over that whole grid.
All right, let's
and
not.
then that outer
All
for
right,
loop
all right.
will go over the whole grid
Yes.
as well.
Yes.
Wait, do you agree or no?
Kind of not. We
Okay,
could.
why not? No, let's discuss it. Why not?
So, the whole thing could be an island. So that means
But
you already count them all.
it'll be like n cubed
No, it wouldn't be cubed. It wouldn't be cubed.
because
It'll be cubed if it's the same rows and same columns.
Nope. Okay. So let's say they're all.
yeah,
Okay.
yeah.
Let's say they're all. You know, and you do the thing. N by n. Okay, if it's all ones,
Yeah, if it's all ones.
then the
outer
helper
for
does
loop.
everything,
Yeah.
and then they're all zero. So that means,
And then the outer for loop does everything again.
Yeah.
Your main function.
so it only does it one more time. It only accesses every other one more time. So that's 2 n by n. Yeah, it's only times 2. It does it twice at that point.
It's 2 and
Yeah,
n?
yeah. What do you guys think? It's 2 n by m, right?
Yeah,
Hmm.
Yeah, because you only do it twice.
it's both ones.
Yeah, it's only one more axis of that value.
Okay, well, why is it 2n by m? I'm not
Okay,
following now.
because like say you're recursively calling on one island, making them all 2s or 0s. That each position is going to be called probably twice, just twice. So a finite number. So it's 2n by m instead of m by n times n by n.
Okay, I'm trying to see. So the part about twice. So
Yeah.
basically, for each, I guess I'm trying to see. Like
Yeah.
for each like coordinate, I guess.
Yeah.
You call it. You basically do it twice.
Yeah, because like it could be a 2, right? So that means we already accessed it.
Oh, okay.
So we're only accessing it one more time. When we escape the helper and we change it to 2 and we're back to this for loop and we're just going row wise, right? It could be that it's a 2, right? And if we find that it's a 2, that means we're accessing the value again.
Oh.
And just once.
Okay.
Just
Oh,
one more.
I see.
Yeah, exactly. So we're just accessing it one more time. I mean, unless you have any
No,
reservations.
I think I agree.
Think you agree? That's just my theory. Okay, so we have 10 minutes, right? BFS?
Yeah.
Okay. So BFS requires coloring. So I'm going to do node 0, node 1, node 2, node 4. This is an undirected, so it's bidirectional. Each edge is bidirectional. You know what that means. So you can get from here to here, here to there on that same edge. And they're all, do you want me to choose another word instead of white?
No, you can go to back to white and black and don't say what you said.
Okay, fine.
Yeah, you did.
It wasn't on purpose. It wasn't on purpose,
I
though.
think he said we're gonna eradicate all blacks.
Yo, Shadi, you're the one implicating yourself now. Now you're the one. Now you're being implicated. See, you're red. Now you're implicated. See, get humiliated.
Now all the flags are discarded.
We're not even monetized. Can't even- Yo, you know what? We should.
That's what he did say.
What?
We should, yeah, for what?
Yo, you know what? You know what? Actually, Google, you should actually monetize this. YouTube, you own YouTube, right? Advertise our own course to FIU students. Do that. You have the FIU students' information. You have their data. Advertise our thing to the students so they can learn from you. Google, you own YouTube, do it.
Are you talking to?
I'm talking to Google right now.
He's definitely listening. He's like, oh,
You care about this club so much, do it, please. Come on. Help the students learn and get engaged by accessing our data that you already have. Oh, and compensating us would be nice too, you know? We'd like that.
send me the timestamp.
Yeah, but yeah. Oh, you probably have it there. What was I? BFS.
Yeah.
Okay, yes. So an adjacency list, do we know what an adjacency list is? I mean, I discussed it with you three, but do you know, Hermes?
Discrete math.
Okay.
I did it last week.
So I would say I have an adjacency list. I'm just going to do it for those that weren't here. And this is node 1 and node 2. And node 3.
Paulina said David is talking to me, lol. Because you were looking right at the camera.
Yeah. Well, Paulina, I was talking to Google, but yeah, I bet Paulina agrees that, you know, Google should access students' data. I mean, look, like FIU has, they're on Gmail, so they're on Google server. Okay.
Thank you, David.
Yeah, no problem. Google's watching us right now. What are we doing? Okay, yeah, this is the adjacency list. This is a graph. Okay? Node, it should be 0. What does this mean? This is, the key is the node, and the value is the list of nodes adjacent to. So n0 is adjacent to n1 and n2. We get it, right? Okay, so BFS. BFS doesn't require recursion at all. It's level-wise. DFS is going through the depth. BFS is going through the level. Yeah.
So with the adjacency list, would you manually make that, or would you have
It's set up beforehand.
like
So
they feed it to you?
yeah, they feed it to you in the LeetCode or wherever you're doing it. So yeah, they give it to you. So I'm doing BFS on a global, and I could have a couple of other global variables. Like I'm gonna do time again, and of course color. Time equals 0. Color equals so they're all white. Yeah.
Oh, by the way, I was gonna say, like, you know, here's a helpful analogy. Like, maybe, like, I work with a tutor. Like, I work with a tutor for this class, and we were talking about BFS and DFS. Like, here's an analogy, like, maybe that you can, you can use to help people think about it. So DFS is like, let's compare it to, let's say you're studying something. So, like, when you're studying something, like, if, let's say the DFS approach. So you're studying something, you come across, like, a concept or something you don't understand, so you look deeper into it. Like, you know. Yeah, like you actually look it up, look deeper into it. But BFS is like you don't. So like yeah, like you come across it, even you don't understand. Like you just, yeah, you just continue going.
Yeah.
Yeah.
That's pretty good analogy.
And then look
Yeah.
deeper into each one.
Exactly.
How do you do the Q? I was just gonna do
Yeah,
it.
it's that first urge is to go deep.
Exactly.
Right.
Yeah, that's pretty good. That's pretty good.
Yeah.
Q
Thank
equals
you.
Q equals. Now you said
Okay.
popping from a Q is n time instead of.
No, it's log.
Okay. No
Log
Q
n.
Q Q Q Q.
Oh,
I'm
from
trying-
Q. Oh, okay.
So
Sorry, I thought
a
you
Q,
meant-
not priority Q. Q Q Q. I'm just gonna do this, right? So how am I gonna start? Okay. So Q, I'm going to append the first node. That's gonna be node 0. How can I get the first element of a hash map? Just 0, right?
What? Access it, yeah, but the index color is 0. Because that's supposed to be the node you start with.
But I have to turn this into a list, no? And the key, I have to extract the key from this.
You're losing me.
Okay, I just want this value. I just want node 0. All I want is this.
Can you not use past the 0?
What do you mean? Hold on. This adjacency list is not a list. It's a dictionary. So I'm trying to convert a dictionary to a list. Get the first one and get the key out of that.
Dictionary, it's not a list.
Yeah, I'm trying to get this key, just the key. Do you know?
I mean, that can be difficult because what if the nodes are like 1, 2, 3, and 4? You want the first one? Like 1?
Yeah, just node 0.
Oh, then do adjacency list dot keys and then minimum.
Okay, wait.
So that's
But it's an
complex.
object, but this is an object, not a number.
N0 is
Yeah,
an
that's an object.
Bro, what are you doing here, bro? Then you need to use a for loop and then do like object.val.
Okay.
Why would it be an object? Why do you want it to be an object?
Wait a minute. Oh, you know what? Actually, I got an idea. To get the first key, I'm thinking.
About the analogy we just said, I don't know. Maybe if you want to use that also.
Like this-
Put it as a comment, like for this recording that we're making today. That's an example.
Yeah, okay. Your tutor gave you that? Your tutor gave you that?
Yeah. Actually, my tutor and I came up with it. Well,
Yeah.
actually, I kind of came up with it first because that actually happened to my grandma recently.
She fell from a tree?
Oh yeah.
Hold on,
Yeah,
you're not
she
gonna
fell
give me
from-
contracts with that? What? Just.
I am lost. I don't know what's going on. What the hell is going on?
How?
I don't know.
How did she even get up there?
She's strong. What are you kidding me? She's strong. She's strong.
It's not only about strong, maybe it's a tall tree, dude. I hope she's okay, Michael.
Yeah,
Well, she is. Yeah, she is. I mean, that's why it's funny. I'm laughing about it now.
Yeah, look at that.
Think it's like that. Okay, that pop 0. Equals. Okay. Blue.
Michael, you're
Well.
your grandma, right?
What did you say?
No, you're like, you really enjoy like.
You okay, Michael?
Okay, yeah.
I'm not indulging in this at all. I don't know what's happening. Apparently, there's something really funny, and
His
I'm
grandma
missing
fell
out.
from a tree.
I'm not laughing at that. That's not funny. That's not funny.
Well, it's just funny from the standpoint of, well, that's how crazy she is.
Okay, well, I'm not laughing. Poor sweet old lady. She fell from a tree. What was I doing? Right. I forgot. Okay. All right, I'm just writing code for you guys. I know I'm blocking it. Okay. Making sure if this is actually. Okay. Thank you. All right. Let's leave it like that. Well, I'm thinking. Here I'm gonna put plus equal 1, and after this, just like this. When do you increment time? Here, Lazaro?
Huh?
When do you increment time?
What are you doing? Oh.
Trying to time it.
Oh, each node should have a time as well.
I know. So whenever while q, right? Do I do it here in the for loop?
Yeah, I think you need to append, get the current time for the current node you're at, and then add 1.
Okay. So this is gonna be 1, right? Then this is gonna be say 2, 3, and then this is 4, right? Because that's when you're done with it.
Oh, you want to count when you're done too?
I mean that's kind of what I do.
So this is your first node?
Yeah.
You're going to pop it, you have this current node.
Yeah. And I
Uh,
color it blue.
You know that the time of this node is 0?
Well, I'm starting at 1.
Okay, you know the time of this node is starting 1, right?
Yeah.
When you append the next one, you take the time of this node, then increment by 1.
So,
So this is going to be 1, you know this is going to be 2.
both of these are going to be 2?
Mm-hmm.
Oh, so this is 2 and 2.
Yeah, because it's BFS, so they both arrived at the same time.
Wait, hold on. How do I keep track of? Oh, okay, so I just put it here, right?
Yeah, when you add it, you need to add first node.
So I don't need an
you
end
need
time.
a tuple.
I don't need an end time. Oh wait, you do need a tuple.
Yeah, you need a tuple.
Oh, okay. You know what? I'm not gonna worry about time. I'll do it next time. I'll do it next time. Okay.
Fun for days.
All right, guys. I'm sorry. I'm sorry I did that. Okay, listen up. Listen up here, folks. Okay, so what happens here? Do you know what happens here? This is BFS versus DFS, this is non-recursive. Okay? So I get the first node right here, right? And I append it to the queue. Or push it to the queue. Okay? So I push this one and then I pop it. And when I pop it, I change it from white to blue. You see it? That means I'm done. I'm completely done with this. Then, for every node that it's adjacent to, right? So, put them in there. Okay? Does that make sense? Any questions?
Not really sure what you did.
Okay. So we have a color, right? So color as the key is the node and the value is white at first. That means they're all unexplored. Here what I'm saying is that I'm having a queue, I'm adding the first node, right? I'm popping it, that current node, then the color of that node becomes from white to blue. Okay? And so basically now I'm going to iterate through every node that it's adjacent to. I don't know. Why are we all laughing now?
I don't know, you were smiling.
I don't know. It's just we're having
Yeah, we
focus. So for every node that this current one is adjacent to, right? I have it here. This is the first node, right? If the color of that node is white, then append it to the queue, which is what I did. Okay. And then next time I come back here and I check the queue is still full, right? I pop the next one to be N1, right? Color it blue. Then for everyone that this is adjacent to, so will be N1, N0 and N3, right? N0 is blue, it's not white, so I don't add it. But N3 is white, so I add N3. Oh, and of course blue was sent, no, N1 was sent to blue. Okay? Okay. So see how like I'm going by level. So this level comes first, everything in this level comes, and then everything in this level comes. Right? Yeah.
So how will you know which ones are the islands in this case? Like, since you have strange nodes.
I guess it has to do with the distance from the land you start from. Right? So
Are there islands here?
well, we could actually maybe I could do that. I have to change this. You know what? It might not actually be that complicated to solve this with BFS. Or maybe it will. I'm actually not sure. Well, I'm not going to actually solve it because I don't think we have time. But I suppose when we add it to the queue, right, we have to add, so, oh my God.
Deep ring for it.
This is good? I don't know.
I'll take care of it now.
Okay, I think it can. Oh.
Actually, that's actually pretty nice.
Michael's having a giggle storm over there. I don't know why. I don't know what's so funny.
Okay.
You know, kind of look like a JoJo character. Just, I do? Yeah.
And you know the games?
The games.
Games.
Oh,
You know how they're all buff.
well, no. After a certain point, they're not buff. They're stylish. Style over ruggedness. Hmm.
This lecture has derailed so much.
I know. I think we're 5 minutes over time.
It's fine. It's pretty short.
Okay. Oh, okay. So you actually did that. So the code I'm just gonna copy off of Lazaro, right? Because I've never solved this with BFS. But anyway, N and M are your rows. Oh, okay. And column. Okay. And you have 4 directions, of course. Choose. I don't know. People are laughing so hard over there. Okay. Oh, I see what you did. Okay. So we have a current, right? We have a current position, which can be decoupled or destructured into, it was a tuple, we destructured into 2 variables, current I position, current J position, right? Equals Q dot pop left. So pop the one all the way to the left because that's the first one that we put in there. And okay, can we just that's a long if statement.
It's the same if statement.
I know it is. Can I just say, guys, remember that if statement we did before? Yeah, we just do it for cur I and cur J.
Oh, add it. Come on, David.
Wait, why? But why are you actually checking it? It shouldn't be a
Those are the
thing.
directions. I'm going over every single direction. I
Wait a
need to
minute.
check.
Wait a minute. I made a mistake. Did I make a mistake? I did make a mistake. I made a mistake, guys. I should be fired for making one mistake.
Well, the president's right here, so.
Yeah, my boss is here, guys. He can fire me right now.
Wait, ask them to complete it.
Oh, right. Okay, so what should we do? This is a DQ, right? And it's on a list, right? We're using a queue, right? So what do we do? While queue means is that while it still has elements, what do we do? What do we check?
Oh, so I guess while it's not empty or, well,
Yeah,
so we're trying
yeah,
to queue it, so basically
right.
we check if there's still stuff in it.
Okay, and what do we get? What do we get when you? Oh, they can still see it. So how do we get the current position? Pop from the left. Okay. And we can decouple it, right? Which means it's a tuple. So we can just make variables out of each values in the tuple. Whether they
What did
be,
you say? It's called decoupling?
yeah, decoupling.
Oh. Oh, I've never heard that one before.
So unpacking.
Unpacking, right. Decouple, unpacking, I think they're the same, right? Because they're coupled together in the tuple. So you just, well, yeah, you unpack it, right? So, because, see, the list is made up of a list of tuples. And each tuple has 2 values exactly. So I'm just getting the first value I'm putting into a variable, and the second value I'm putting into another variable. I'm unpacking.
Okay, okay.
You get it?
Oh, well, yeah, okay.
Are you sure you get it?
So basically you just, so you have ij in the whatever. In the
Yeah,
top,
yeah. And I'm getting the
basically you
current
just take
I
them out.
and the current j, right?
Ah.
I'm setting it to variables.
Okay.
Okay, and if blah, 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 fine, whatever, I'll do it. I'll do it, whatever.
Ask them.
Okay, guys, what do we need to check, right? About the current positions, like we did before. What do we need to check about the positions?
Whether it's in the bounds.
Yeah. So check if 0 is in the bounds. No, cur I is in the bounds of 0, and n. N is the number of rows, right? And what else? For j too, right?
Yeah, same for J.
Cur j m this time. And what else, guys? That we're at a 1. So map equals 1. Okay, so now we passed all. What happens now? What do we do?
Well, we probably have to change it to 2 or to stay in.
To what? Well, okay, yeah, we have to change it to 2 or 0. I'm going to do what I did and change it to 2. So j equals, what is it, 2. What does this mean, guys? What does this mean? What am I doing here?
You just, you're gonna check the pressures.
Oh, they don't see it. Move it down. Okay, so for each direction here, right? So new I, new j, new movement of I and j, right? We're going to
Okay.
it's okay.
This one typing in the chat.
Okay. So now we're gonna append a new tuple, right? Well, we're gonna append 4. And why 4 tuples?
4 durations.
Yeah, because we're going in 4 directions. Up, down, left, right. Right? And here, the size of this list is 4 of dirs. So it will be cur I plus new I and cur j plus okay. Yeah. That I think I'm gonna write more down. Yeah. Yeah, like that. Put it back. Okay, that was cool. So now we have defined our BFS function.
You still laughing at your grandma?
Okay, now that
I
you
can't
say it.
believe that, bro. Why would you do that?
So he's gonna tell us, yo, this happened like last year. Still laughing at it.
Michael, please, it's not funny. Your poor grandma.
It's funny that he laughs. So.
What is that? No, I don't think that's funny, guys. I think that's very, I don't know, guys. I don't have a sense of humor, guys. Sometimes life is just dull. And it's not funny. Yeah, it's philosophy. Okay. So now, right, we're going to do the row-wise thing. And for each one we find, we're going to do BFS from there. And the point of BFS is pretty much the same thing we were doing before. Do you remember what we did before? We turned all the adjacent ones to 2s. This is going to do that too. Okay? So we're going to add each direction, right? And if we find that it doesn't follow any of these, we don't do anything. We don't add, right? We just pop it and that's it. So every time we actually find an adjacent one and it's a 1, it's actually going to do all these things of adding the directions. Make sense? Okay. This actually, now that I think of it, this works exactly the same as what we were doing before.
Yeah, so you didn't know how to do it.
Okay. No, I just didn't know about this way. Yeah, but it makes sense. Okay, so what do we do here, right? Just like we did before, we have to check that map I j equal 1, right guys? Then we do it. We do BFS on that position. J. And of course, we also increase the answer by 1. Plus equals 1. And we return the answer here. Oh, God. This was long. Okay, do you have any questions about what we did? You get it? It makes sense? Do we get what's happening here? What's happening here? So we're going by level, right? So we add all the directions, right? And if it's a bad direction, we don't actually append anything to it. Only if it's a 1 do we actually add adjacent coordinates. Does that make sense? Okay. And that's this part. And this will work for all the adjacent ones, turning them into 2s, such that we don't have to explore them again. Okay? So they're all conjoined. And our answer will be properly, it's going to be the number of islands there actually are. So yeah, this is this one, which I think the other one's simpler, right, guys? The other one's a little simpler than this. Yeah. Yeah, they agree with me.
No, I agree as well.
Yeah.
It's nice knowing both ways.
Would they ask actually? Are they gonna ask?
It doesn't matter if they ask, it's what did they do. So you know it either way.
So
Even if you don't know it, it's just interesting too.
yeah, it is interesting.
The same
No,
way
this
as
is
doing-
this is very interesting. I didn't know that.
The same way as doing DFS, but instead of recursively with a stack. You know how to do it all 3 ways. Just helps.
Yeah, technically, it's like a single source, right, from the grid, and you're going through all directions. It's like a tree. It's like not a minimum spanning tree.
It's DFS or BFS, so it always makes a tree.
Yeah. So BFS and DFS always makes a tree from the source. Right. And that's kind of how it is. All right. So I think we're going to conclude it because
Way past time.
we are way past time. We are 20 minutes past time.
Yeah.
So thank you for sticking out so long. I really appreciate you guys, staying here and supporting all of this, everything we do. We hope that you turn out for this Friday. Also this Friday, we're having a binary search night. Huh?
Oh, never mind. I thought you were talking about the event this Friday.
Was it,
HTML, CSS.
yeah, we were having HTML, CSS workshop in PG6 116, no? 112? PG6 112. All right.
I mean, it's on the posters. So.
Yeah. So just go to the posters in case or
online.
Check our Discord and our Instagrams, and we are gonna come out with LeetCode problems very soon.